So we are talking about avalanche effect, and we are saying that in avalanche effect, even what avalanche effect basically says is that if there is a single bit change in the pre-image, it should trigger an avalanche that will jumble the other bits. So suppose this hello gives us a message digest, which is this 2ch something. Now, even if one bit of the pre-image or the message is changed, we change E from I. So this becomes, suppose now there is a single bit change here. So what it will do is it will cause an avalanche effect in this message digest, and it will change the entire message. So suppose this H is represented using say 4 bits. So you will have 4 bits are same, and after that all your message will be changed. So this is known as the avalanche effect. Now avalanche effect is most commonly used in almost every blockchain. If you try to implement your own blockchain, this effect is used. So you have a block and you have some transactions inside your block, and you compute the hash of this block. So you compute the hash and you call this hash as, suppose you call this as block hash. Let me erase this. So as I was saying that you have a block here, was block 1, and you compute the block of this hash. You have another block, say block 2. So what you'll do is you will use the block hash of block 1 to link this block 1 to block 2. In the same manner, you will use the block hash of block 2 and you will put this block hash in block 3. So now this is your message. Suppose this is your message. Now you change just one bit in this message. So if you change one bit in this message, this block hash will change. Now since this block hash will change, this block 1 will no longer link to block 2. And since this block 1 hash changes, now one important thing to remember here is, now suppose this is your block 1, you compute the hash and you call this block hash. You store this block hash here. Now when you compute the block hash, you will also use this field also to compute the block hash for block 2. Now since this field changes, when you compute the hash, this field will also change. So what will happen is there will be a kind of a domino effect or an avalanche effect which will falsify your entire chain if you make one bit of alteration in your blockchain. So here we can see that this hash function ensures that whenever there is some change in your input, it is noticeable and everybody who is using that chain can verify that okay, some change has been made. So this is what an avalanche effect is. So 3 requirements that we mentioned were, first is that it is a one-way function. Second is it exhibits an avalanche effect. Third important requirement of any cryptographic hash function is that the cryptographic hash function needs to be collision resistant. So let us see what we mean by collision resistance. So suppose this is your hash algorithm. So for our let us for our ease, let us say that it is a 8-bit hash algorithm. When we say our hash algorithm is an 8-bit hash algorithm, the total number of hash digest that can be generated is 2 to the power 8. So 2 to the power 8 is 256. So we are saying that our hash function, whenever we pass a message, is also called the pre-image, through this hash function, we can get a total number of 256 message digest. Or hash values. Okay, so suppose our input is, say, so this is our input, and when we pass it through this hash function, we get an output as, now we say that this is a 8-bit hash function, so let us say that we get how output as, we get an 8-bit output. So this is a 8-bit message digest. Suppose we have another message, say we pass it through the hash algorithm, and this also hashes to the same message digest. So when two different messages, this is a message and this is a message, when two different messages when passed through a hash algorithm give you a same message digest, same hash value, then we say that collision has occurred. So when two inputs to the hash function give you the same output, it is known as collision. So the third and a very important requirement for any cryptographic hash function is that this a cryptographic hash function should be collision resistant. That is, we should not get two input values that would give you the same hash value or the message digest. So collision resistance is one important requirement of a cryptographic hash function. So now here we can see that our hash function, that is this 8-bit hash function, is not very collision resistant, because a very small message, two very small messages passed through this algorithm gave us collision because they both were hashing to the same value. But in reality, the hash functions used are very large. So here in our hash function, there can only be 256 possible digests. So we have a very small range here. But generally, the hashing algorithms that are used will have a very vast range of message digests. So we'll see that shortly. So when a range is small, we could always guarantee that a hash collision will occur by simply iterating through the 257 inputs. So in blockchain, the most common hashing algorithm that is used is a 256-bit hashing algorithm, and this is known as SHA 256. Now, this algorithm is used in Bitcoin also. So, when we say that we are using a 256-bit hashing algorithm, now we will not have a 8-bit message digest, but instead we will have a 256-bit message digest, and it is not a 8-bit algorithm, it is a 256. It is a 256-bit hashing algorithm, that is SHA 256. So when we are talking about SHA 256, the range of the message digest, that is the size or the number of message digests that you will get from SHA 256 is 2 to the power 256 plus 1. Here also there will be plus 1. So you will not get 256, but you will get 257 values. So the number of message digest that you can obtain from a 256 hashing algorithm, SHA 256 hashing algorithm is 2 to the power 256 plus 1. So when we are talking about things at this scale, so you will have to try 2 to the power 256 plus 1 numbers in order to get at least one collision. So we all know that hash functions must have collisions. After all hash functions have a finite output size, yet they have infinitely many number of possible inputs. So we are saying that a hash function is limited by its input size. So you can have any number of possible inputs, like any length of possible input, but you will always get a finite output size, which will be determined by the hash function. So here in our case, we are saying that we are using a SHA-256 hash function. So when using SHA-256 hash function, our length of our message digest will be 256 bit, but the number of message digest we can get from SHA 256 is 2 to the power 256 plus 1, and this is a very 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 big number. So just to give you a perspective, this number 2 to the power 256 plus 1, so the number of atoms in the universe is roughly 2 to the power 260. And what we are saying here is that the range or the size of the message digest that we can obtain from SHA 256 algorithm is 2 to the power 256 plus 1. So we are saying the number of atoms in our known universe is 2 to the power 260, and the number of message digest obtained from this SHA 256 algorithm is 2 to the power 256 plus 1. So for all practical purposes, this 2 to the power 256 is so big, that is that it's almost effectively innumerable. So while we know that a collision must exist, we are never going to find one in the lifetime of a universe. And indeed, a collision has never been found for SHA-256 algorithm. So we know that SHA-256 is a collision resistant algorithm. So SHA-256 is a one-way function, then it is collision resistant, it also has avalanche effect, and the other three properties, that is, it is deterministic, it has a finite size output, and it is uniform. So this is all about your SHA-256 algorithm or hash functions. So hash functions are very secure. They are easy to compute in one direction, and they're very difficult, almost infeasible to compute in the other direction. And it is very difficult to find two messages that will hash to the same value. Now, there are three properties of any hash function. We have already talked about collision resistance, that it is very difficult to find a message M such that hash of that message is equal to hash of some other message. So we don't have, like, it is very difficult to find two messages M and M dash such that hash of the message M and hash of the message M dash is equal. So this is the collision resistant property of cryptographic hash functions. Then the second property is the pre-image resistant property. So given a hash of a message, it is very difficult to find some other message such that hash of that message is equal to the hash of the message that we know. So we are saying that we have hash of some message. We don't have the original message, we have the hash of the message. So it is very difficult. It is difficult to find even the message itself if you only have the hash. And to find some other message whose hash will be equal to the hash that we have is almost impossible. So a good cryptographic hash function should be pre-image resistant. Third important property is second pre-image resistance. Given M, it is difficult to find M dash such that hash of M dash is equal to hash of M. So we are saying that if you have a message, it is very difficult to find some other message whose hash values are equal and messages are not equal. So very important here, important thing to remember here is we are saying if we have a message M, it is very difficult to find some other message M dash which is not equal to M such that hash of M dash is equal to hash of M. So if any cryptographic hash function does not meet any of these requirements, the hash function is said to be not a good hash function, and it is not used in any like any digital signatures, any kind of software implementation, or any certificates that are generated. So a hash function, a cryptographic hash function, would fail if it does not satisfy any of these, at least even one of these properties. So if a hash function does not satisfy even one of these properties, then the hash function should fail. It will fail. It is not used in any kind of software implementations. So next we'll talk about digital signatures. Now, a digital signature is equivalent to a handwritten signature, and it is kind of an electronic verification of a sender. And the main purpose of using a digital signature is to authenticate that sender has sent the document that has been received by the receiver. So we are saying that a digital signature is used in order to ensure that a document wasn't changed after it has been sent by the sender. So digital signatures are very useful feature for sensitive data that may get changed either due to like some network error, some error during transmission, or there may be a eavesdropper or due to some kind of man in the middle attack. So digital signature is useful feature for sensitive data that may get changed during transfer over the network or due to some kind of attack. So let us see what digital signatures are. So digital signatures are most commonly used in financial transactions, legal bindings, and they're used in software distribution and many other cases where it is important to detect forgery or detect any kind of tampering. And they're also used because they are difficult to imitate and can be time stamped. So suppose you're sending a sensitive document over the internet. You want the recipient of the document to know that it was you who sent that document, and you would also want to ensure that the document gets to the recipient in the very state you send it in. That is, you don't want any alterations in your document, you don't want any alterations in your document, and you also want the recipient or the receiver of the document to know that it was you who sent the message. So in both of these two cases, that is to ensure that your document is received without any alterations and to have the like the receiver know that you are the sender of the document, we make use of digital signatures. So let us see how digital signatures work. So digital signatures use encryption decryption technology, which is known as asymmetric cryptography. So in asymmetric cryptography, what you do is you have two algorithms. One is for signing, which involves a private key, and one is used for verification, which will involve the public key. We'll see all of these shortly. And output of the signing process is called the digital signature. So a digital signature is an electronic signature that can be used to authenticate the identity of the sender of the message, who is the signer of that document, and it is also used to ensure that the contents of the message or the document that has been to the sent to some receiver has not changed during transmission. So let us see how digital signatures work. So as stated, digital signatures use asymmetric cryptography. Now, asymmetric cryptography is also known as public key cryptography. So here in public key cryptography, what happens is you have two keys. Remember we talked about secret keys. So here also in digital signatures, you use asymmetric cryptography, which is also known as public key cryptography. And here we make use of two keys. We have a public key and we have a private key. So let us say we have a sender. His name is Bob. Bob is the sender. Now we are saying that we are making use of asymmetric cryptography. So here we will have the private key of Bob. So this private key will only be known to Bob, who is the sender. So here we have a sender who's Bob. and we have a private key with Bob. We have a receiver. Let us say the name of the receiver is Alice. So Alice is the receiver here. So now Alice will have Bob's public key. So in asymmetric cryptography, we make use of two keys. So here what Bob does is he will generate two keys. One is the private key, another is the public key. Then what will Bob do is Bob will keep the private key with himself. He will not share this private key with anybody, but he will give his public key to Alice. So Alice will have Bob's public key. Now, suppose Bob wants to send a message. So here we'll have a message. So this message is a plain text message. So we have a message and it is a plain text message. So what will Bob do now is Bob will pass this plain text through a hash algorithm. So we have a sender Bob. Bob generates two keys. One is the private key, one is the public key. He will keep the private key with himself and he will make the public key available to Alice, who is the receiver of the message. So Bob will create a message which is in plain text. What we'll now do is he will pass this plain text message through the hash algorithm. And we know when we pass some message through the hash algorithm, we get a digest. We get the message digest. So let us say our message digest is some random number. So this is our message digest. Now, what Bob will do now is he will pass this message digest through an encryption algorithm. Will pass this message digest through an encryption algorithm and he will use this private key. So now Bob has encrypted the digest with his private key. Now this message digest has been encrypted with the help of private key using the encryption algorithm. So now what we get is a digital signature. So Bob is the sender who has a private key. Bob writes a message, which is a plain text message. He passes that message through the hash algorithm. He will get a message digest, which is this message digest. Now, what he'll do is he will sign this message digest with its private key and make use of some encryption algorithm. So Bob is encrypting his digest with his private key, and this encrypted digest is now known as the digital signature for the message. Now what Bob will do is Bob will send this digital signature and this message, the plain text message. this very same plain text message. So what Bob now is doing is, Bob sends, is sending this plain text along with the digital signature to Alice. Now this plain text is same as this plain text. So after computing the digital signature for his plain text, Bob is sending the digital signature as well as the plain text to Alice. Now, when Alice receives this, now when Alice receives this digital signature and the plain text, she will do two things. Now notice that here the message is not encrypted. We have issued a digital signature and we are sending the message. So here our only focus is on digital signature. So after encrypting the message digest using his private key, Bob receives a digital signature. Now Bob is sending the digital signature along with the plain text to Alice. Now when Alice receives them, she will do two things. First is, Alice will decrypt this digital signature. So as I was saying, that Alice will do two things. The first thing that Alice does is she will decrypt this digital signature. And for decrypting this digital signature, she will use the same asymmetric algorithm that was used here. So she will use the decryption to decrypt the message. So Alice will decrypt the digital signature using Bob's public key. So when we were encrypting the message digest, we were using the private key. Now when Alice now has the digital signature, she will decrypt the digital signature using Bob's public key. Now when she decrypts this message, she will get the message digest. She will now get the message digest. So after Alice, what she does is she makes use of the digital signature, passes it through the decryption algorithm, and uses Bob's public key to decrypt the digital signature. And once she decrypts the digital signature, she will get the message digest. Now, next thing, that is, once Alice gets the digest, she will check the integrity of the message. So this message, she will pass this message through a hash algorithm. So she will pass this message through the hash algorithm. It will be the same hash algorithm that was used by Bob for passing the plain text and creating a message digest. So she will use this plain text, she will pass it through the hash algorithm, and she will, once it is passed through the hash algorithm, she will get the message digest. So once Alex gets the digest, she will check the integrity of the message. So she will check whether both of these message digest She will check whether these digests match. So here we can see, yes, the digests are matching. So if, let us take a scenario, if she was not able to decrypt the digital signature. So we received a digital signature. Alice tried to decrypt this digital signature using Bob's public key, and she was not able to decrypt the digital signature. So then Alice will know for sure that the message did not come from Bob, because a message that is encrypted using Bob's private key can be decrypted using Bob's public key. So this is one important property of any asymmetric algorithm, encryption algorithm, that when you encrypt a message using a sender's private key, you can decrypt the message using sender's public key. In our case, our sender is Bob. So encryption happened through Bob's private key. When Alice tried to decrypt the same digital signature, she made use of Bob's public key. So if Alice were not able to decrypt the digital signature using Bob's public key, then she knows that the message did not come from Bob, because only Bob's public key is able to decrypt the digital signature that is generated with the help of his private key. So in our case, what Alice did was, Alice hashed the message, the input message, the plain text, with the same hash algorithm that was used by Bob. And then she compares the result to the message digest that she received. So she made use of the digital signature, and using decryption and the public key of Bob, she received a message digest. Then she passed the plain text that was also sent by Bob, and she passed it through the same hashing algorithm that was used by Bob during sending the message. And she receives some message digest. And then she compares the results of both these message digest. Now, if they are equal, Alice can be confident that the message has not been changed, since Bob signed the message and Alice is able to decrypt the message using Bob's public key. But in case the digests are not equal, Alice will know that message has been changed in transit. So this is the entire process of digital signature. Now, to summarize, we have a sender, Bob. Bob makes use of public key infrastructure, public key cryptography, which is also known as asymmetric cryptography. Bob generates two keys. One is the private key and one is the public key. Bob keeps the private key with himself and gives the public key to Alice, who is the receiver of the message. Then what Bob does is, Bob encrypts the then what Bob does is, he passes the plain text through the hashing algorithm to receive the message digest. Now Bob encrypts this message digest with the help of his private key, and this encrypted digest is the digital signature. Now Bob sends both the digital signature and the plain text message to Alice. Now, when Alice receives the digital signature and the plain text, she does two things. First, Alice decrypts the digital signature by making use of Bob's public key. So, when she decrypts the digital signature using Bob's public key, she gets the message digest. Second, what Alice does is, she will check the integrity of the message. To check the integrity of this plain text message, she passes the same plain text message through the hash algorithm that was used during sending and was used by Bob. So she passes this plain text message through the hash algorithm and she gets some message digest. Now Alice compares both these message digest, the one that she received and the one that she computed. So she compares the result that she has received. Now, if they are equal, she can be confident that this was exactly the message that was sent by Bob. But if this message has somehow changed during transmission due to anything like uh, either due to some error during transmission or some eavesdropping or some kind of attack, this plain text, the digest that should will be obtained from this plain text will not match with the one that was obtained from the digital signature. So if the digests are not equal, the receiver, that is Alice, will know that the message has changed in transit. So this is the entire process of digital signature. So digital signature usually involves two processes, one performed by the signer, that is the sender, other by the receiver of the digital signature. The digital signature creation uses the hash result derived from and unique to both the signed messages and a given private key. The digital signature verification is the process of checking the digital signature by reference to the original message and the given public key, thereby determining whether the digital signature was created for that same message using the private key that corresponds to the referenced public key. So we have seen all of this, that during verification, the receiver verifies the digital signature by passing the original message through the hash function, and thereby she'll get a digest, and the digital signature is decrypted with the help of the public key, and this will ensure that the whether this digital signature was indeed created by the signer or the sender of the message or not. So this is the exact same example that we have taken. Here they are talking about a lawyer. So you're assuming that you have sent a legal document to your lawyer, and this lawyer is in another town. And your lawyer wants an assurance, or you're trying to give assurance to your lawyer that whatever you have sent to him has not changed during transmission, and you're also giving an assurance that it is really you who has sent the some legal contract to your lawyer. So you will copy and paste the contract into an email node. On email also, you have special softwares which will allow you to obtain a message hash, which is the mathematical summary. So we are sending a contract. So here you will have a message digest of your contract. Then you encrypt the message using the private key. And in a real case scenarios, what you have is you have some private public key authorities who, like in Bitcoin also, when you download the Bitcoin software, you will get a private key, sorry, a public key, and using that public key, you can generate your private key. So the private key is only known to you, but we could also have a cloud server which will have the public key, which is kind of your address. That is when you want to send coins from one address to another address, that public key will be your address. Okay, I want to send like 10 Bitcoins to this address. So the address will be the public key of the node or the any machine which is using the Bitcoin software. So you obtain the message hash, you encrypt the hash using the private key, and the your encrypted message digest, encrypted hash becomes your digital signature for the message. Then you send both the digital signature and the message to your lawyer. So in order to ensure that the message is intact and that message is indeed from you, the lawyer will again calculate the hash of the received message by using the same hashing algorithm. And he will also use your public key to decrypt the message digest in order to get the, sorry, you will use your public key to decrypt the digital signature to get your message digest. Now, he has the digest from the digital signature. He has also calculated the digest from the received message. And if the hashes or the message digest match, the lawyer will be ensured that okay, A, the message is correct, B, that indeed you were the one who sent this contract to your lawyer. So you are verifying two things with the help of a digital signature. You are verifying your identity, that is, the lawyer is able to authenticate that it was really you who sent that message, and you're also ensuring the integrity of the message. That is, whatever you sent, whatever contract, whatever legal binding you sent to the lawyer, he has received it as it is, like the same way that you sent it. So you are verifying, you are achieving two things with the help of digital signature: A, authentication, and B, integrity. So this is the same uh, process to depict how digital signatures are created and verified. We have already seen this. We have a plain text message, you pass it through a hash algorithm, you get a message digest. You encrypt this message digest with the help of the private key of the sender. When you encrypt the message digest with the private key, you get a digital signature. Now, this digital signature, along with the document, is sent to the receiver. So, this end of the process is known as the creation of digitally signed document. So you're sending your document as well as your digital signature to the receiver. Now, the receiver will use your document, pass it through the hash function, and it will get a hash code. In the same time, he will use your digital signature, decrypt your signature with the public key of the sender. That is your public, you are the sender. So he like the lawyer will decrypt this signature with the public key, your public key, and he will also get some message digest. So if calculated message digest match, then it means that you were the sender of the message, and also that the message has not altered during transmission. So this phase is known as the verification phase of the digital signature. So creation of the digital signature takes place during at the sender side, and verification of the digital signature takes place at the receiver's end. So I think we'll stop here for now. If anybody has any doubt, you can ask. Otherwise, you can drop your enrollment numbers in the in-call messages and we can exit the call.